Morning. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my atmospheric waves training. This will be part two. And in today's video, I'm going to cover short waves. All right, so what exactly are short waves? Short waves are baroclinic features that are embedded within the long wave pattern. So we have these little features. Typically, you'll see short waves on the 500 millibar weather chart, which is at about 18,000 feet above the ground. And also, you can see short waves at 700 millibar on those 700 millibar weather charts, which is about 10,000 feet above the ground. But they're these baroclinic. Now, when I say baroclinic, we're talking about some sort of temperature advection is involved in these particular short waves. Baroclinic, there it is. We have height contours and the isotherms that are crossing each other, and we have that temperature advection occurring, just like I just mentioned. And the short waves are relatively small as compared to long waves. And there's what I just mentioned about where we can find short waves. There's a difference between a major short wave and a minor short wave. A major short wave will show up on both of these weather charts, the 700 millibar as well as the 500 millibar. You'll see the major short waves. The minor short waves you may only see at one of these levels. Another chart used that we can identify short waves on is the 500 millibar vorticity chart. Short waves are going to be located near maximum and minimum vorticity centers, the X and the N. Remember, we talked about that in my previous training video about vorticity, where we talk about vorticity maximums represented by the letter X, which is usually in the color red. And then you have the vorticity minimum areas, which are located by the letter N, and that is typically in blue. All right, so we generally have the 500 millibar vorticity chart. We can identify these short waves, and we get vorticity advection to occur in combination with the temperature advection. For satellite imagery, how do we identify short waves? Short waves appear as small changes within the cloud pattern. Major shortwave troughs and ridges are going to move generally within the long wave pattern. They generally follow the polar front jet stream, where that jet stream is, follow the polar front overall. I don't know why I put this twice, but for some reason I did. When you're building this type of stuff, it's interesting because, you're really building and typing, and, sometimes you don't mean to like duplicate it here, so I apologize for that for sure. But the speed of movement of short waves depends on where the short wave is located within the long wave pattern, and also the amount of temperature advection that's ongoing. Short waves move up to 15 degrees of longitude, or roughly 900 nautical miles per day. Short waves can also have a major effect on the long wave pattern, and we kind of talked about that in my part one of atmospheric waves video. So if you have not already done so, I would definitely recommend taking a look at atmospheric waves part one, the long waves, because I talk about how these short waves kind of play into the long wave pattern, how they can deepen long wave troughs, how they can build long wave ridges. Now, the long wave is barotropic, and I mentioned this in my last video, barotropic, where you do not have any type of temperature advection. Barotropic, no temperature advection at all. And it's barotropic, the long wave, and when a baroclinic short wave moves into that barotropic long wave, the flow of the long wave is disturbed, and you get temperature advection, which is introduced to that region of the long wave, and it causes what's known as baroclinic instability. And when you get this little short wave to move through that long wave pattern, a lot of times it can disturb the long wave pattern to the point where you get baroclinic instability, and that instability will then enhance your vertical air motions, which changes the intensity of upper level features and also helps develop surface pressure systems, those highs and low pressure systems. There's a lot to digest on this slide, but I will tell you this is a very important slide. Let's examine some of these key points, okay? I'm going to draw it out for you. This first bullet at the top, the very first bullet, short waves can have a major effect on the long wave pattern. Let's say, for example, I'll show you an example of let's say this is a long wave trough. So this is LW, long wave trough, okay? And then we'll do a long wave ridge, which is an upside down shaped U pattern. So this is also a long wave ridge. All right, so I'll tell you what, we'll label long wave trough as LWT, and we'll label the long wave ridge as LWR. All right. The first bullet here, short waves can have a major effect on the long wave pattern. That's absolutely true. I'm going to do my short waves as dash lines, okay? So let's do the trough first. And let's say I have this short wave trough represented by this dash line on my diagram here on the left. So let's say the solid red line here represents my short wave trough axis. So we have a short wave trough that is moving down the backside of this long wave trough like that. It's going to deepen this long wave trough when you get the short wave trough moving in. Now remember what happens ahead of short wave troughs. Let's go ahead and draw it out here, over here on the far left. This is what happens with short wave troughs. Out ahead of the short wave trough axis, you have upper level divergence. Remember this in my previous training video? Right at this location ahead of the short wave trough axis, you get upward vertical motion or rising air, so UVM, and then you also get upper level divergence, ULD. So we're losing mass at the top of the air column out ahead of the short wave trough axis, and then you also get vorticity advection in the form of PVA, positive vorticity advection. All right, that's all ahead of the short wave trough. PVA, upward vertical motion, the air is rising ahead of short wave trough axis. You're going to get clouds and precipitation usually. And you get upper level divergence aloft at the top of the air column. So that's the chimney effect. We're losing mass at the top of the air column. We're going to enhance or increase our low level convergence and accelerate our vertical rising air motion. Okay? So think about it now. This over here on the left that I just did, those are the features out ahead of a shortwave trough. Now, we represent the shortwave trough with this dashed line. We have it superimposed over the solid red line, this long wave trough. And out ahead of the shortwave trough, we have the PVA, we have the upper level divergence, rising air motion, and then we have upper vertical motion, okay? So as this vorticity advection, the PVA, moves through the base of the long wave trough, it's going to result in a deeper long wave trough. It's going to go from the initial diagram I had to this new diagram, a deeper long wave trough, as the short wave trough moves in to the west of the long wave trough axis and kind of dives into that long wave trough. For a ridge over here on the right, now let's examine, I'm going to do dashed lines again. It's going to represent my short wave, okay? So these red dashed lines are my short wave. In this case, I have a short wave ridge, this little kind of seesaw jagged line here represents my shortwave ridge axis. Now this shortwave ridge is moving into a long wave ridge. What that's going to do over time, now let's just examine shortwave ridges now, okay? So I'm just do a little refresher review here. Let me get my eraser out here, okay. Let's get rid of the trough here over here in the middle, all right? Now, with shortwave ridges, let's examine that. So let's say this is a shortwave ridge. Okay, we have our ridge axis is denoted by this little sawtooth line. Out ahead of the ridge axis in this location, you are going to get NVA, negative vorticity advection, which is going to enhance your downward vertical motion. It's going to be associated with surface high pressure. You're also going to get upper level convergence. So you're adding mass to the top of the air column. ULC is upper level convergence, NVA for negative vorticity advection, and you're going to get DVM with ahead of a shortwave ridge axis. So DVM, downward vertical motion. All right, so think about this as we go through it. Well, so we have a shortwave ridge moving into the long wave ridge. That's going to build this long wave ridge like this. See how it builds? It's going from the graphic on the left to the graphic on the right, we have a building ridge, long wave ridge, and we get a short wave ridge to move through it. All right. Of course, we also have this temperature advection as well that's occurring in association with these shortwave troughs and these shortwave ridges. All right, so here's your shortwave. The thermal trough, by the way, that's your temperature trough or thermal trough, is going to lag behind the height contour trough. So this diagram on the right, the solid dark lines represent your height contours. Your red dashed line represents your isotherms, lines of equal air temperature. You notice how your isotherms are in 5 degrees Celsius intervals or increments. All right, but you notice how this black dashed line here, this represents your thermal trough. And then you have basically, I'm sorry, let's see, thermal trough is lagging behind, yeah. So this is your height contour trough here. And then this is your thermal trough back here. So your temperature advection, your thermal trough, your temperature trough is going to lag back further to the west as compared to the height contour trough. So we're basically bringing this area of warm air advection out ahead of the shortwave trough. And you notice how these dashed red lines cross these solid black lines of height contours. That means we got some sort of temperature advection ongoing. We have cold air advection on the back side of the shortwave trough, and we have warm air advection out ahead of it. Moving on. Major shortwave troughs, what exactly are these? They usually reflect from the upper levels right down to the surface and can be associated with jet streams and jet stream maximum. We talked about these jet maximums on a couple of videos ago. We talked about the vorticity and the XN relationship. Please feel free to review that video. Ahead of the shortwave trough, we have upper level divergence. We kind of hit that already. That produces increasing or rising vertical air motion, upper vertical motions, which results in, as air rises, it cools, condenses, and forms clouds and precipitation. So out ahead of shortwave trough axis, that's where you're going to get your most active weather. And that's why it's so important to look at these features at 500 and 700 millibars to see, hey, where are these short waves in relation to my long wave pattern? Where are these short waves in relation to my location? What kind of weather can I expect to see as results? Now, behind the shortwave troughs, you get upper level convergence, which occurs, which is going to result in sinking air motion behind the shortwave trough. And weather will improve as that shortwave trough moves through due to that subsidence or sinking air motion behind the trough. So sometimes you hear the TV meteorologists say, hey, we have an upper level disturbance, upper air disturbance moving in. They're referring to these short waves. All right, so here's the major shortwave troughs example. Nice diagram here. Clouds and precipitation. Now this solid dark line here, this represents your shortwave trough axis. The really dark line is the shortwave trough axis, and these other solid dark lines represent your long wave pattern, your long wave trough. You're getting rising air motion, upper vertical motion ahead of the shortwave trough axis, out ahead of it right here. You're getting your clouds and precipitation out ahead of that, okay? Now behind the shortwave trough axis is where you're going to, back here, you're going to get more of the sinking air motion. With major shortwave troughs, there's 3 situations that directly impact the intensity of them. You can get thermal advection, okay? So you can get thermal advection. You get confluence and difluence, or upper level convergence, upper level divergence. And then you have to look at the shortwave trough's location in relation to the long wave pattern. Okay, so is that shortwave trough moving into the base of long wave trough? It's going to deepen the long wave trough. This is going to amplify the overall or deepen the long wave trough and result in an intensifying storm system at the surface. Or is it over here instead? Cold air advection occurs into the backside of the trough. This is going to cause the trough to deepen. Thermal trough again lags behind the height contour trough, allowing the cold air advection CAA to occur. Anytime you increase your vorticity advection, okay, so you have PVA and you got PVA out here out ahead of the shortwave trough axis, and then you also have WAA, warm air advection, so you have warmer air moving in. Boy, my letters are not good, and I apologize for this, but they look kind of funky. Anyway, when you have both positive vorticity advection and warm air advection, you're going to get upward vertical air motion in the atmosphere. Behind the trough axis, you're going to have NVA, sinking air motion, but you're also going to get cold air advection back here behind the trough axis. All right, so there's a difference here between PVA, NBA, and cold air advection and warm air advection. Diffluence will help to deepen the shortwave trough by removing mass from the air column. If the shortwave trough moves into a long wave trough axis, the shortwave will deepen due to increased cyclonic curvature in the long wave trough. All right, so we talk about diffluence this term. That's basically the chimney effect. So we're taking air and we're removing the mass aloft. This is our surface. We have increasing low-level convergence, the opposite effect at the surface. That causes the air to meet and rise here. All right. You increase this removal of mass aloft, the diffluence. This is going to intensify your shortwave trough, and it's also going to deepen your surface low pressure system. All right. Temperature advection plays a big role in filling a major shortwave trough. If you get the warm air advection into the trough, this will fill it and decrease the trough's amplitude. If the trough moves into a long wave ridge, that's also not a good situation for a shortwave trough. It's going to weaken or fill the trough. The associated cyclonic curvature into that long wave ridge will decrease. You get more anticyclonic curvature will begin causing the trough to fill. And then if the trough moves into a long wave ridge, the associated cyclonic curvature will decrease and anticyclonic curvature will begin. This is basically saying the same thing as my previous bullet here, but in general, just think about this. For major shortwave troughs, you want cold air advection into the trough. That will intensify it or deepen it. If you get warm air or warmer air moving into the shortwave trough, it's going to fill it. All right? And again, it's very important to look here at the position of the long wave trough, the shortwave trough. It's important to look at the position of the shortwave trough in relation to the long wave pattern. And here's an example. Speed of movement will increase as the shortwave decreases in size. Kind of getting back to long waves is very similar with short waves. Which one of these do you think, let's just look and examine this. Which one of these shortwave troughs do you think will move quicker? Do you think it'll be A here on the left, or do you think it'll be B? Which one's going to move faster? Now, A, we have increased amplitude. It's deeper. The shortwave trough's deeper as compared to B. So the deeper the amplitude, the slower. I'll represent slower with the letter S. For trough A here on the left, it's deeper. It's going to move slower. Whereas the trough here at point B has much less amplitude. It's going to move, I'm going to put the letter F here, F for faster. All right, so take a look at this. At the top, cold air advection, colder air moving into the trough axis, represented by the letter CAA, cold air advection. That's deepening this long wave trough axis, got it? And that's going to result in the system moving to the east at 25 knots. All right. You increase the amplitude of this thing's going to move even slower. Look at now, it's moving 15 knots to the east, increasing the amplitude. Kind of what I covered down here, but just kind of showing it up here as well. For major shortwave ridges, this baroclinic feature often reflects the surface as high pressure system. Ahead of the ridge axis is excessive upper level convergence that supports the surface high. Downward vertical motion is created by this upper level convergence, which warms and dries the atmosphere, producing clear skies. This is the damper effect. Behind the ridge axis, a shortwave ridge axis, is upper level divergence, warm air advection, and increasing clouds. So let's think about this now. All right, so we have a surface high pressure system. There's going to be a major shortwave ridge that is going to be tying directly down to this surface high pressure system. Okay, and out ahead of this ridge axis, a shortwave ridge axis here, you're going to have negative vorticity advection. You're going to have downward vertical motion. The air is going to be sinking, supporting this high pressure system. You have upper level convergence ahead of the major shortwave ridge axis. And again, it's going to support the surface high, this H right here at the surface. So you're going to get fair weather if you're located out ahead of these major shortwave ridges. So with major shortwave ridges, they're enhanced by warm air. So ridges, the upper level ridges like warm air advection, WAA, moving into the ridge axis is going to build the ridge. Upper level ridges build if moving into an area of confluence aloft. And you'll notice this specifically in the wintertime if you get a jet maximum or a jet streak, and you get increased upper level confluence or convergence aloft, the damper effect. If you have more air coming in at the top of the column and converging like this, as compared to at the surface, let's say my arrows represent the magnitude, by the way. So I have shorter arrows at the surface. I have basically longer arrows and a stronger or greater magnitude of the upper level convergence here. That's going to result in more air being pumped downward in the atmosphere, and that's going to increase my surface high pressure system. If the shortwave ridge moves into a long wave ridge axis, the increased anticyclonic shear will help the shortwave ridge build. So what that's saying is, here's my long wave ridge, and then here's my dashed line again representing my shortwave ridge. Here's my ridge axis. Let's say the shortwave ridge is moving into this long wave ridge. It's going to allow the anticyclonic curvature of both the shortwave ridge and the long wave ridge are going to kind of help and enhance each other. And that shortwave ridge will build. And as that ridge builds, the amplitude will increase. In other words, this is going to get taller, and the speed of movement is going to slow. Here you go, warm air advection into the ridge axis. Ridges, upper level ridges love warm air advection. It allows heights to rise, which means the ridge will build. Look at the difference between the ridge here on the left and the ridge here on the right. Notice the amplitude. How tall this thing is much taller on the right as compared to this on the left. You have warm air advection, like I said, into the ridge axis. This is a less amplified ridge here on the left, which means your speed is going to move quicker as compared to the slower movement of this building ridge on the right. Now we only have 15 knots to the east for the speed of movement for this highly or increased amplitude building ridge on the right. Warm air advection and this shortwave ridge, the sawtooth line here, are going to be responsible for building the overall ridge. And then the opposite effects occur for major shortwave ridges as far as weakening them. Cold air advection into the ridge axis causes upper heights to fall, and upper level ridges want heights to rise. So they really like warm air advection. Diffluence aloft will weaken the ridge by removing mass from the ridge faster than is being put into it. And then if the shortwave ridge moves into a long wave trough, the anticyclonic curvature will decrease and cyclonic curvature increases. And if the ridge weakens, it will decrease in amplitude and again speed up. So it's basically the opposite of what we saw here of how you build ridges. You build major shortwave ridges with warm air advection moving into the ridge axis. If you increase your convergence aloft, you're adding mass over here on the right. It's your damper effect. You're bringing more in than is being pushed away or pushed out at the surface. And then if the shortwave ridge moves into a long wave ridge axis, that's increasing the anticyclonic curvature. It's going to help build the shortwave ridge. The opposite occurs now with do I have a diagram of it? No, I don't. But the opposite occurs here with a major shortwave ridge if you want it to weaken. If you get cold air advection into that ridge axis, again, it causes upper heights to fall, which is exactly opposite of what you want for a building ridge. And then the diffluence aloft. So now instead of confluence or convergence aloft, we have diffluence. So the air is spreading apart in this vertical air column here. That's going to result in a little bit of an increase in rising air motion here and low level convergence. Vice what you want with a ridge. You want upper level convergence, these two arrows coming together. So if the shortwave ridge moves into the long wave trough, let's see what happens here. So here's your long wave trough, and now we have a shortwave ridge basically moving into this long wave trough. This has anticyclonic curvature, the shortwave ridge, red dash line. And then of course we have cyclonic curvature here at the base of the long wave trough. So it's going to result basically in the anticyclonic curvature of the shortwave ridge decreasing, and it's going to weaken. All right, that wraps up part 2 of my training on atmospheric waves. Part 3, we will delve into barotropic systems, okay? We'll talk about barotropic lows and highs. We'll talk about baroclinic lows and highs. We'll talk about the differences between them in part 3. Hopefully you got a really good information out of this training video on shortwaves. Now, I'm going to tell you this right now. I'm hoping to maybe just tie everything together when we're done with all this, okay? I want to show you actual weather chart and show you all these different pieces and how they can come together to enhance storm development or decrease the chance of storm development. It's a three-dimensional slice that we need to look at in the atmosphere. We talked about short waves in general. These are hugely important as far as providing support for our surface low pressure systems and surface high pressure systems. The short waves are baroclinic features, and they're just smaller wavelength features embedded within that longer wave pattern. They kind of flow and follow the jet stream, okay? And as they transition, you're looking for shortwave troughs, you're looking at shortwave ridges here. As these systems move from west to east in the mid-latitude westerly belt, they support the surface pressure systems. All right, and that's why it's so important to look at the atmosphere in 3 dimensions. You have to look at the 700 and the 500 millibar weather charts to identify these short waves. You can also look at the 500 millibar vorticity chart to locate, hey, where is my maximum vorticity center, letter X? Where's my minimum vorticity center, letter N? Where's my vorticity advection occurring? Where's my temperature advection occurring in addition to the vorticity advection? We can identify short waves using satellite imagery. A lot of times what you'll see is like some enhanced areas of bright white color on IR imagery. And these are basically your short waves. You may have this huge broad, let's just say it's an upper level low, and then you just have this cyclonic curvature, this broad cyclonic curvature around this low pressure system, cyclonic flow, and you get these little disturbances. These are your shortwave troughs that kind of just rotate through the long wave pattern on the backside of these huge, upper level lows. So in IR imagery, I've seen it plenty of times where they show up as these bright little areas, and that's your short waves. Overall, they follow, again, the jet stream, the long wave pattern. These short waves do. They follow the polar front jet stream. We talked about the speed of movement. Really depends on, where's the short wave in relation to the long wave pattern and the amount of temperature advection involved. And you do notice, these things do zip along quicker, 15 degrees of longitude, or roughly 900 nautical miles a day, which is very rare. Let me go back here. And I want to just tell you, let's see, 15 times 60, yeah. Okay, so if you ever wanted to convert, how do we get 900 nautical miles out of this bottom bullet here? Because short waves move up to 15 degrees of longitude. So if you take 15 times 60, you get 900. All right, so 15 degrees of longitude equates to about 900 nautical miles. And then short waves, we talked about them in today's training video. We talked about, moving through the long wave pattern. Out ahead of shortwave trough axis, we have warm air advection and PVA. Behind a shortwave trough axis, we have NVA and cold air advection. You notice that the red dashed lines, the thermal trough is offset from the height contour trough. The thermal or temperature trough lags behind because this is an out of phase situation here in this diagram on the right, where you have the red dashed lines, your isotherms, lines of equal temperature, crossing the height contours, which indicates temperature advection. We talked a little bit more about upper level major shortwave troughs, kind of like where the clouds of precip will occur out ahead of them, the shortwave trough axis. And then we talked about, the intensity of these systems. And that's all I got for now, everybody. I know it's a lot to digest, but these are just so very important, these concepts in meteorology. All right, that wraps it up, and I will get on to the barotropic and baroclinic systems in atmospheric waves part 3 soon. Until then, everybody, take care and God bless everyone.